Okay, welcome to the session 2 of the lecture 7. And before going on to the break, we were talking about the scenario when it is not 100% fully defined that in which state we would be when we perform an action. And we have seen that for those kind of problematic scenarios, it is better to go for an AND or search tree, and that we have discussed very recently. That here, when you are into the state, a particular state, you can take multiple actions, but sometime when you reach to the state where multiple states are possible, then you have to find out the goal for each of those states. So similarly, if you into the state 1, if you take the sub, then you have two states, 7 or 5. 7 is still a goal, since itself a goal state, you need not to do anything. But for the 5, you have to find out the solution. So therefore, the solution doesn't end when you take the only stuck action. It goes down till you specify that I am going to take the right, then suck, then all other things. So we have seen two problems. One, when the space was continuous. Second, when sometime it is not confirmed that in which state you would be. It's a non-deterministic environment. Next thing that we are going to see, that when you are having partial observations, searching with the partial observation. What do you mean by partial observation? Means you don't have enough sensors that can tell you that what is your state. So what is the problem? Problem is that you don't know in which state I am. So if you don't know in which state I am, then how can you suggest that which action I can take? See what is the big problem. When your percept does not suffice to pin down the exact state, means when you don't know that in which state you are. Are you able to understand this? You know that what are the action that you can take, but I am not telling you any about your state, in which state you are. So how can you reach to the goal state? Is there any possibility that you can reach to the goal state? Can anybody tell? Do you understand what I told you? That can you visualize the problem? Can you visualize the environment? Can you visualize the environment? No? Please tell me so that I can explain you much. Otherwise, I would assume that you are understanding all these things. You understand the environment? People are telling yes. So what I mean that your agent, whatever percept is available, is not able to 100% be sure that in which state he is. Earlier example, however, it was non-deterministic, but here you are knowing that I am into state 2, I am into state 8, I am in state 4, I am in state 1, 6. But here you don't know that what is your state. Then how would you go ahead? The most problematic thing is a sensorless. Let's assume that you don't have any sensor. Looks like that such a scenario is a hopeless scenario, but it's not. Sometime you can, let me just explain you. Sometime you can find out the solution into even this kind of hopeless scenarios. So this, let's assume the completely sensorless scenario when you don't have any sensor. Then I'm going to tell you this particular move: right, suck, left, suck. Okay. So can you imagine that what is going to happen? Okay. I'm telling you that you would be 100% going to get the solution due to the goal state, because here I'm not telling you that whenever you are performing some operation, there is non-determinism. Okay. Now we don't have any non-determinism. That is not a problem. The problem is that we don't know in which state we are. So what I mean by this? Therefore, consider this thing: right suck, left suck. Okay. So in whatever state you are, right means that if your thing is if your vacuum cleaner is here, you say right, what would happen? It would remain into the same place. If it is here, then if you say right, what would happen? It would come into this thing. So therefore, by doing this operation right, what is going to happen? It is confirmed that your vacuum cleaner is here. Okay. Then you say suck. Suck means what? That there is some dirt that has been cleaned. Okay, that has been removed. Okay, this is the suck, and then you say left. You are not concerned that whether there is some dirt or not. Even if there is no dirt, if you say suck, there is no problem. Room would be clear. Now I am telling left. What does left means? It would come into this room. So the scenario is this, that this room is clean and your vacuum cleaner is here, and now you are telling the operation suck, means this room is also been cleaned. No problem. So it means that what is going to happen, that both the rooms are clean and your your agent is into this particular room. Are you with me? You understand this? You understand this thing? That even if it is a sensorless scenario, there could be some sequences that can guarantee to reach into the state 7, that is a goal state. I think this time it is goal 8. So we have reached in the goal state 8. Okay, so I would correct this. I think there is a small mistake. So this is a goal 8. Okay, goal state 8. So this traversal actually means whenever we are going to change the state from one place to another, it actually goes through the belief states. Belief state means, what do you mean by belief state? Belief state means we believe that after doing this right, we would be into this state. We believe. Our belief is, what is the belief state? That when you apply this particular operation that is right, what is going to happen? Your vacuum cleaner would be here. It may be possible both rooms are clean. What else can be possible? Your vacuum cleaner is here, there is a dirt. Your vacuum cleaner is here, there is a dirt. Your vacuum cleaner is here, both places there is a dirt. So there is a club of these 4 states you are in. When you are applying this action, you assume that you create a hyper state that you are going to call a belief state. So you are going to be into that belief state. You are telling that after applying this particular thing, I am going to be into this particular state. Understand? Easy? Easy to understand? Okay, are you with me? Can anybody write yes? What are you doing? Nobody is writing. Thank you, thank you. Okay, please keep motivated me. Okay, keep me motivated. Okay, so next thing that I want to tell, that these belief networks, how many possibilities are there? Okay, belief network I'm telling. Okay, belief states. If I say the belief states, how many belief states are possible? So you see that one example, and in one example what was possible. So let's assume that we have, how many states we have? We have 8 states. 1 2 3 4. 1 2 3 4. We have seen the 8 states. What are these 8 states? These are the 8 states. Nah? These are the 8 states. So how many belief states I can form? Okay, so I can take 1 of them, I can take 2 of them, I can take 3 of them, means all possible subsets. So how many subsets is possible? 2 to the power 8 subsets are possible. Okay, but interestingly, all of them are not reachable, because sometime we can see that all of them are not reachable. Although we have 2 to the power 8 number of state, but only 12 out of them are reachable. Means sometime it may not be possible that you could reach all of them. So these 12 states are shown over here. You can see this, that in one place there, let me see that hours 1 is available or not. Whatever controls that earlier we have seen, you created one. So what was this? I don't know what is the number. So you just find out what is the number. Hours 1 would also be available over here. Okay, try to see that which one is the hours 1. So here 1357. Okay, and from here if you take the suck, you can reach to this 517. Then you take left, you can reach over here. You right, you can reach over here. You can take left, or you can any of these states. So you can see now this maze, you can understand all these places. Similarly, you can go into this way. Okay, this state to this state. If you want to go from here to here, what you can do? I think you can go take the right turn. You come here. From here to here, no possibility. Then how can you go? I think from this is any of these places you can go take to this state, then go to this state, go to this state. You cannot go into this state because maybe possible something. Okay, but what is your target? The target is to reach into 8 or 7 this location. So to reach over here from any for any of the place you start, you can reach over here. You can see that there is a path from which you can reach over here 7 or 8, and 7 and 8 are also connected. So you can reach to any of the final states. So are you with me? You understand this complete idea? Do you understand this complete idea? The idea is this, that although sensors are not able to tell you, but from your hypothesis you can find out some belief states, and using those belief states you can traverse from one belief state to another belief state, and then also sometime you can devise their connection such that you can always reach to the goal state. Sometime it is not always. I cannot guarantee. So we have seen the third problem, that when we have things are only partial observations. Now we are going to see the fourth problem. One more problem, that online search an unknown environment. Sometimes it happens that the environment is unknown to you. You don't know what is there. Okay, and therefore agent interleaves computation and actions. Interleaving means when this we means this. Initially agent into some state, he don't know that what is going to happen when I'm going to take this particular step. Essentially what I mean, that the environment, you don't know about the environment. You don't know about the environment means what? Whatever state is specified to you, you know that what action you can take, but you don't know that if I take this particular action, what would be my next state. So this is the problem. So you one by one you start exploring the state. So what you take the action. You initially went to some state, you take the action, and then observe the environment, what is there. Then you compute the next action. Observe the environment. You compute the next action. What should I take? And sometimes it is clear that what action you should take. Sometimes it is not clear. Then you take some random action and you go ahead. Okay. Online search is necessary for unknown environment. So this particular methodology we are going to call as a online search environment. So let's give you an example. That is a very straightforward, simple example. And let's assume that this is the maze, and these are some places where these are the tiles, and your agent or your robot is standing at this starting position location. And our target is that your agent should reach it to this particular place. So what is the way that it can take the right, up. So this is how you can reach. But it is not told to him that where to go. So what he would do, he would, in this state, he may take the up action. Then after taking the up action, he start taking the again up. He would not be able to execute that action. So he understand that from this state, from 2 1, he cannot take this particular 1 2, or he cannot take this action. Then left hand side, he take the right and left. He cannot take those actions. Then he have understood that I cannot take this. What is the next remaining thing? So he take the down. Then he take the down. Then he from here he knows that I can go up. But he can. Then he decides, no, I would not go up. Then he goes into the right. Then he will find out the new things. Then one by one he start creating the environment. And after doing multiple number of time, he would be able to understand that what is the environment, and then by chance he would be able to reach to the goal state. Whenever he goes to the another cell, he checks that what is the state. If it is a goal state, it would stop, and if its task is to explore the things, then he would keep on doing. Okay, so one such method is the random walk. Okay, what is the random walk? What is the random walk? Can anybody tell? Okay, I'm not going to much detail. It's a mathematical theory behind it. I'm just going to introduce you this problem, and I encourage you that you go and read by yourself. Let's assume that there is a city, okay, and in the city there are some roads. You know that there are some lots of roads, and there are crossings also. So there would be some crossings, okay. there would be some crossings, there would be some roads, somewhere there would not be a road. So you see that there are some roads. And let's assume that a person lives at this particular place, okay, at his house, and he is at this particular location, okay. He is at this particular location, and he want to go to the house, but he somehow lost the sense that where to go. He don't know that where to go. So what is the way? He would go for the random walk, because he understand, whenever, let's assume that he knows that whenever he reaches to his house, he recognizes that, okay, this is my house. So therefore the problem is, the solution is that he would randomly select that whether should I go to this place or not. He would come here. At this place he find out that there are three ways. It may be possible that he may go back, or he may go into this way, or he may go into this way. Similarly, he is performing everything at every place. For example, when he is here, he can go back, he can come down, go forward, go up. Anything he can happen. So there is a mathematical formulation that I encourage you to read, that when the problem things are defined, there is some fixed number of steps, that at least it will be very large number, that after these many number of steps he would be reaching to at least once into this particular location. Expected that in these many number of steps he would be able to reach over this. So mathematical formulation is random walk. This is beyond the scope of our study, but if you are interested, we can take it up. If you like to read it, please let me know, so that we can, in the next class we can cover it up. But this is the one way. So random walk says that if you don't know about the environment, you may take because whenever you're standing here, whether you should go up or down, you don't know. So you randomly pick that where should I go. So you go into that direction. From there you take the random walk. And similarly, after some time, you would be able to reach this particular location, and your work is done. So you understand? Do you understand that what I wanted to tell you? That sometime the environment is not known to you. On those places you have to go for the online search, and online search says that wherever you are into some state, you choose some action. How to choose that action? There could be some guiding factor also, because you may find out there could be some ways to figure out that which side you should go most. But let's assume that it's not there, then you can randomly select any of the outgoing path, and you go ahead, and at the end you would be able to discover all the environment. After these many number of steps, you would be able to explore all the environment. Okay. So you know that when an unknown environment is given to you, you can apply this online search strategy, and by this you would be able to explore the environment. And when you would be able to explore the environment, then you can plan that what is the right way to go ahead and find out the solution. Okay, but please note down that any deterministic algorithm means any algorithm, there could not be any algorithm that can avoid dead end in all the state space. Means sometime it may be possible that in this particular diagram, it may be possible that if I say that this particular location, if I say that this particular location is a trap. Okay, if you are randomly going around, if you come here, then you would not be able to go out of this place. It may be possible that there could be some places. So such as let's assume that this is a police station, and since you are drunk, you are moving anywhere. So if you come here, the policeman would catch you, and he would tell you that you stop going here and there, and you just sit here. So this is a bad situation. So so what you want? You want to avoid this place, but that is not possible, because sometime it may be possible that because you are performing the random walk, sometime since you reach at this place before reaching this place, it may be possible, but it is just a possibility. Sometimes it may be possible that you reach this place earlier. I want to say that there is no such algorithm that can guarantee that you would not reach to that particular police station, you would reach your house first. There is no such algorithm that can give you this kind of guarantees. Okay, so we have seen this particular problem also. So these are all the different problems. Then we are going to reach to the very interesting place, and now this This is called the a very interesting topic that we want to open, that is called the adversarial search. Okay, and it is a kind of game. Okay, so here what happens that you are not alone in this environment. You are not alone. Two or more, two or more agents are there, and they are playing the game. What is the game? Means what? Let's assume it is a game of chess. So you are having a turn, then you are doing something, and then it says turn of the second party. He would be giving having some, he is doing some progress, and therefore you can assume that both of them has conflicting goals. Means you want to win, but he also want to win. Therefore, he want to defeat you. So his goal is to defeat you, and your goal is to win yourself. Okay. So both the agents are working into conflicting things. Sometimes it may also be possible that you are doing cooperative, but here we are talking about adversarial search, where the second person is actually not good. He want to make you lose the game. Okay. So in the multi-agent environment, most of the time we have this thing. So we want to see that what are the right ways to make things for the game. And in the artificial intelligence system, most of the time we actually confine ourselves to a very small area, because when we sometimes for our understanding, we want to solve the simple problems, and using the solution for the simple problem, you can consider the difficult problem ones. But very initially, you would not pick any problem that is very difficult. So our assumption is that the environment is deterministic. We have seen that how to go for the non-deterministic, but now the environment is deterministic. Means if you say that I am going to progress this particular pawn, horse, or whatever thing, so it is going to get progressed. Okay, so deterministic, fully observable. You see what are the board position and where all the your items are. Things are fully observable. Turn taking, you also assume that it's your turn, then it's a turn of the next agent, and you are exchanging the turn one by one, and you are playing the game. It's a two-player game. We are also simplifying this thing. Not more players are there. It's a zero sum. Zero sum means actually zero sum is actually constant sum. Means at the end, when the game is going to end, the profit that is actually distributed is constant. It may be possible that when you win, you will be getting 1. If he wins, he is getting 1, and you are getting 0. So therefore, what is the summation? Three possibilities are na. When you play the game of chess, there are 3 possibilities. What are the 3 possibilities? That player 1, player 2, that he wins and therefore he loses. He loses and he wins, and there is a draw, both the draw. So you see, you can apply that when he wins, he get 1 rupee, he loses, he gets 0 rupee, and he wins, he get 1 rupee, he loses, got 0 rupees. Okay, and when they get draw, they give, both of them give half of the rupees. So what does it mean? It means that what is the summation? Summation is 1. Here also summation is 1. Here also summation is 1. So this is a constant summation thing. So we say that the things are fixed. There is no change, and therefore sometimes we call it zero sum. Okay. So adversarial search game environment for which we are going to talk, they are actually are having these kind of properties. So let's just solve this particular problem. Okay, so let's pick one problem. For example, chess has the roughly branching factor of 35. Sometime the branching factor is 35. How many? Can you tell me how many 8? So the 32. Branching factor is 32. Means what? Means 35 moves you have. Whenever you are given a turn, you have 35 things to move. Sometimes it may be lesser, but average, on an average 35 moves you can move, because pawn you can take either one square forward or 2 forward, and similarly others have a different thing. So you can find out that there are 35 different moves are possible on an average. and when you play the game, it is expected that you would be running 50 such moves to play, because when you start you have to go for the 50 moves to win or lose on an average. You understand this? So can you find out what is the search tree? How many nodes would be there into search tree? Because initially if you take this thing over here, so how many nodes would be there? Can anybody tell me how many nodes would be there? Can anybody tell how many nodes would be there? Please tell how many nodes are there. Okay, that is not difficult to tell. Okay, it is written over here also that whenever you are into, let's assume that you are into this state, how many things are possible? 35 things are possible, and then here again you are 35 turns are possible. So and it is also telling that this is the first move that you move. This is the 0th move. Okay, this is the first move you move. This is second move. Similarly, you go for the 50 move. Okay. So how many moves you have to move? 35. You have to move 35 to the power 50. Okay, multiplied by 2. Because why 2 multiplied? Because this is your first chal, but your second chal would not be here. Your second turn would not be here. Your second turn would be here. Okay, second turn would be here. This is the opponent's first move. Okay, opponent first move. This is not you. This is you. This is you. So if you go for the 50 turns, so the game progresses 100 number of times. So therefore it is 35 to the power 100. Looks like it is 100 to the 10 to the power 154. My God. However, the graph has 10 to the power 40 nodes only. Why? Because many other time you see that here when you progress this particular place, this has already been arrived. The same board position is here. So 10 to the power 40 board positions you can see. So this is a fairly large number, and therefore nobody can think that I can construct all these things into the computer and I would be able to search the best possible thing. Finding optimal move is infeasible, but still we need to find out. We need to develop some ability to decide that what should be our next thing. Okay. So when we go ahead for the how to go ahead with this is our subject matter. So when we want to decide these things, so we want to define the game into the formal way. So let me define these terms so that it becomes clear for you. Game is in between max and min. There are two players. There are two players, max and min. I am going to give them name max and min, and the reason would be clear to you very soon. The one person is max and another person is min, and you are the max and the opponent is min. So you want to maximize value because for your value you want to maximize, but the opponent want to minimize that. He want to put something so that your sum is going to be minimum. Therefore, I am going to call him the minimum, and you are the max one because you want to maximize the value, whatever value that you have. Okay, max move first. That's the first thing. S0 is the initial state of the game, and then player S means, if I say player S means whose turn it is. Player S would give me define which player has the move to start. Action S means into if in this state it tells that what are the legal moves, because some legal moves would be there that would not be into the other state. So what are the legal moves? If I call action says, it is a set that defines that these moves are possible. Result SA means tells that if you go what is the next thing that you are going to get into this state. If you take this particular move, define the result of the move, what is going to happen. Terminal test S means tells that whether the game is over. If you are into this state, whether the game is over or it is still on. You have to go ahead. Utility SP, it tells you that what is the value that you are going to get. Utility means it is a function that gives you reward, means how much you have. The some states you may not be reward. If you are going to be into the final state where there could be various final state, okay, into the chess there could be various board positions where opponent does not have the king. All those places you are actually you won those things, therefore you are getting the reward 1. So some places the reward is +1, some places the reward is 0, some places the reward is half. Sometimes places you are actually loser, sometimes you are winner. Then on those chess positions the reward is +1. And for other places you can compute that what is the possibility that I would get to do that particular place, and based on that you can find out some value, and therefore utility can be assigned to all the states. Okay, but sometimes it depends upon the your problem formulation. Sometimes you say that I am only going to assign the values to the final state only, and not in between things are not having anything. Sometimes you can find out using probabilities. You can assign that if you are into this state, most probable that you are going to win the match. Therefore, some value is there. So this particular example actually try to give you an understanding of the same thing that you by yourself understand, that it's a game of tac to. I think you know this game, na? Cross and zeros, tic tac toe. The spelling is wrong. Tic tac toe, huh? I think you know the spelling should be tic tac toe. So this is tic tac toe game where initially you have 9 positions, and if you have the chance to put a cross, so you can put at these any of these 9 positions, and then it is a chance of is max chance, because your chance then you are going to reach into this position. Then it's mean chance, he would put 0 into these places. Here he can put the 0 in how many ways? 8 ways. Here he can again put the 8 many ways. So initially you had 9 ways to put, but he have 8 only 8 ways to put the zeros. Then you have 7 ways to put the cross, and then min max min max max min max min. You can find out. Similarly, you reach to some position where either he wins or you win, or there is a draw. So search tree for the game has less than factorial 9 nodes, because you know that at this place there are 9 places. Then everywhere there is a 8 place, so you multiply with the 8. Then all these states would have 7. So you see the factorial 9 number of states are possible. They are this much, 362,880 number of nodes are possible, and that is what the important part is here is that if you want to find out the solution, so how would you find out the solution? Now this time in the terms of games, what is important that everything is not there, because when you are here, you have you can choose any of these things, because it's your turn. You can choose any of these board positions, but after that you cannot choose, because it's now when let's assume that you have gone for this. Then you cannot say that next is what is the next stage going to be. Next stage, all the possibilities are there. That is actually given by the min. The min would challenge you and try to minimize your possibility of winning. So he would be putting anything anywhere. Okay, so you cannot tell that into next step this is going to happen. So therefore you cannot have a direct solution. You have to define, you have to discover a strategy. Means if he is going to put this thing, then I would put this. If he is going to put this thing, then I am going to put this. So you have to formulate a strategy, not a particular solution. Instead of going to the solution plan, you have to decide a strategy. Okay, you have to decide a strategy. You please try to understand this particular very important line, that you have to find out a strategy. Okay, so when you decide, come up with a strategy, this is going to be your solution. Then only you can play the game. So the whole purpose is to learn for a strategy into this game. It's into the game environment. we go for the strategy. Please understand this thing. In the game environment, we go for the strategy. So it is very much analogous to the AND OR search, and here the max plays R means the you play R, because these are things, and you are going to take one of them. But min plays AND goal, and means he can go anywhere, so therefore you have to find out the solution for all the possibilities, so that if he goes this, then how I would win, for this how I would win, for each of the things you have to find out the solution. Are you with me? Are you with me at this particular line? Very important thing I am telling, that analogous to the AND OR, it is analogous to the AND OR search. Max plays a all role and min plays AND role. This is a single line that is very important. I want you to understand this. In case you have any doubt, please ask me. What does it mean? Max plays R and min plays AND. What does it mean? Do you understand this, or should I explain more? Do you understand this? Max plays R and min plays AND. This is a very important line. Let me tell you that this is going to be a very important line, and how min plays AND. Do you want to make more explanation? Do you want more explanation? Okay, let me give you. This is a very important line, okay? And let me tell you, if you understand this, then everything would be very clear. So therefore, I want to once again tell you that what I mean by this. Okay, so what line I want to highlight? I want to highlight this line. Max plays R and min plays AND. I want to highlight this line. Okay, who is Max? Can you tell me who is Max? Max is you. So you are here. You are here. You are Max. You are Max. You are playing R. What is meaning of R? Means you can take any of these things, because this is the possibilities. Let's assume that you have chosen that I would take this particular move. So you are playing R move, means one of the moves that is available. You are going forward using R, means for all the possibilities you are choosing one of them. But this min player means the people who is next to you, he can take how many? 1, 2, 3, 4, 5, 6, 7. He can give you 7 challenges. Okay, so he can give you single challenges. You cannot only select this one to give the answer. You cannot select this second one to give the answer. You cannot select the third one to give the answer. You have to provide the answer for all these things. Meaning you have to develop the solution, so that at the end there is you are winning. At the end you are winning. At the end you are winning. So you are actually going to divide the solution, so that at the end you are winning. So your strategy should be such that in all the cases you should give the solution. And this is precisely the same thing that we were talking about before going to the break. We were talking the same thing. Okay, same thing now we were talking about here, that if it is the AND thing, then you have to find out the solution in each of these paths. But if it's the OR thing, that you can safely take one path whichever you like, and you can go ahead and find out the solution. Because if you take this thing, you want to find out something, so that you reach, for example, go to the right suck and go to, then you will be reaching to the goal state. So you can go ahead in this way. You can take right, you suck, and then you are into the goal state. But here again it is an AND, so you will be into problem. So you have to find out the solution for this thing as well. So what I wanted to tell you, that that into this scenario, the same thing is again coming to you, that tells that Max is playing OR and min plays AND. So therefore the tree that is going to be is a AND OR tree, and you have to find the solution into the similar way. Okay. So 2 half move is 1 ply, means as I told you that when you take a move, it's a 1 half, and your opponent takes a move, then it becomes one complete circle. So 1 ply means your move and your opponent move. So you by 1, 2, 3, 4 you go ahead. So it is called 1 ply. So Can you find out what is the optimal strategy over here? Okay, so let's assume that you want to find out optimal strategy. What is this tree? What is this tree? Okay, okay, here what it is, somehow somebody told you that what is the utility function. Okay, what is the utility function? That let's assume that these are the trees, means these are the trees, and you are going to start the, these are the trees. Okay, these are the future trees that you are going to be. You are into the state A. Okay, so you can, let's assume that A1 and A3, these are the two moves available to you. So whether you would go for A1 or you would go for A3, this is what the question is, because you have to solve so that you can decide that where should I go. So to go this, you see that what are the possibilities with your opponent. What are you see that what are the possibilities with the opponent. I think I missed this, A1, A2, A3. These are the three things are possible. Okay, sorry for this. These are the three moves, A1, A2 and A3. Three moves are possible to you. So you would see that in all these cases, what is what your opponent would do. So what your opponent would do, he would do something. Okay, if you take A1, your opponent is going to do something. Okay, so your opponent, you would see that what is the profit of the opponent. Here, opponent has the three possibilities. He can take the route B1, B2 and B3. Okay, let's assume that somebody has computed that if he takes the B1, the utility would be 3. If we take B2, utility would be 12. If we take B3, utility would be 8. And you know that he is adversary, therefore he want to minimize that value. Therefore he select this particular thing, B1. He would select B1 because B1 is minimizing the thing. So he would put 3 over here. You see, he puts 3 over here. Similarly, if you take the A2, so you would be into this scenario. Here your opponent would take the move 2 because 2 is the minimum out of 2, 4 and 6. So this value is here. You see that he is going to take the move 2. Similarly, if you take the A3, you take the move A3, then your opponent is going to, out of 14, 5 and 2, he is going to take 2 because 2 is going to minimize the thing. So he is going to minimize this thing. Now you know because he is going to have this particular 2. So you want to make him into the bad scenario because if you go into this, he would reduce the value to the 2. So he would not go to this is the scenario. You say that no, I will not go here. I would not either go here. I would go here so that he makes 3. If he gives you the value 3, it is your profit. So you want to maximize on this line on the 3, 2, 3. You 3, 3, 2. You have put the 3 over here. As you know, the maximum you can get is 3. So what move you should give? You should make. What move you should make? You should make the move to A1. You should make the move to A1. You understand this? That given this tree, if it is your chance, it is your turn of Max. Max would see that what is the opponent is going to do, and opponent is always going to give you the bad thing because if he were into this scenario, he would take this particular path. Then your value is going to be 2. So you therefore want to go take the A1 so that you reach 2 over here. Given the game tree, optimal strategy can be determined from min-max value of the each node. You want to find out the min-max value of each the node. And now we are getting some more technical. I want to introduce one more terminology that is called the min-max value. What is the min-max value? Min-max value for A. What is the min-max value for A? So it is if it is a terminal node, if it is the leaf node, terminal node, final position, then whatever the, if it is a terminal test, then what is the utility of S means whatever the final value is over here. And you know the into the game of chess that we have discussed, the final values are 1, 0 and half. So based on the board position, you would be able to find out that what is the my value. So if it is a terminal board position, now game is over, then you would be able to get the exact value. Otherwise, for example, this is not the final location. Your game is on, so you are going to find out For all the actions that are possible over here into this state, in the state as you are, so for all the actions that are possible over here, for all the actions you find out what is the min max into that particular state. Means when you come over here, you apply this action, then what is the value, then you apply here, what is the value, apply here, what is the value. Okay, you want to find out the maximum. If the player is max, if you are max, then you want to find out what is the maximum over here. If you are minimum, you want to find out what is the minimum over here. Similar thing, minimum of this, if player is minimum, the min max value would be decided by the minimum of the peoples who are below him, and otherwise it is the maximum of the peoples who are children of this. I think this formula is pretty clear. It's not a difficult formula, very easy formula. And therefore, if you apply the formula, we have discussed enough about this, then the action A1 is the optimal choice. You know, action A1 is the optimal choice. Essentially, optimizing the worst case outcome of the max. You see in the worst case, what would happen in the worst case scenario, because this is a worst case scenario, because everywhere the opponent is making your life hell. It's not telling what is the best case. Best case would be that opponent is very dumb, and therefore he would give you the chance of, so that he in this case he would take the D1 route, give you the 14, so you take this thing. So it is the best case, but you are not going to into that scenario. You are seeing what is best case scenario, and you want to maximize that particular thing. I think it should be clear to you. Is it clear? Can anybody write yes? It's very straightforward. Can anybody write yes? Is it clear? So this is how min-max algorithm works. So you know the min-max algorithm, how this algorithm works. You want to, this is the algorithm that whenever a state is given, your task is, whenever a state is given, your task is to find out which particular action I should take. So this algorithm says that the state is given and you want to find out which particular action I should take. So you are trying to find out the maximum, which are all the actions. For all the actions, you see the what are the what particular action maximizes your value. You are going to take that value. So here this A1 maximizes your value, but to find out this 3 again, you have to go deep to find out here. So therefore this is a recursive thing, that you min value, you want to find out the minimum value out of all the results that you get whenever you into this state whenever you apply the action, state and action, you see that what are the results, and then you want to find out the minimum out of that. So this is very important to find out this thing. So it is a recursive procedure. So min value, you see that min value is here. Again the same kind of thing, that if you are into the final state, then you say that utility is my value. Otherwise you start with the minus infinity value, and for all the actions that are there, you find out the maximum value. And in the next state, because you are going to the min, then you again there is some max. Okay, so here you want to find out again this would be the call for the max, then you would go down to the tree. Same thing, means you want to find out maximum value out of all the minimum values, then you again go for the minimum value. So it's a recursive definition until you find out the answer. Recursion proceed all the ways down to the leaf, and this is the most difficult part. This recursion goes down and try to explain get all the values, and therefore the time complexity is order of b to the power n. What is m? B is, you know, the branching factor. Any place if the branching factor is b, means next b number of things are next to the any node, and then m is the solution depth. How many different what is the height? How many turns are required? So if m number of terms are required, so therefore this thing is going to take order of b to the power n. That is exponential, and therefore it's very difficult to find out the solution. So hope it is clear to you, and we are going to stop at this moment. And although we have more topics available, but I think it is not fair to cover these topics today. Next topic, let me just give you an idea. If you understand this part, so you see that this is the biggest problem. B to the power n is the biggest problem. So sometimes there are some ways by which you can actually reduce the sum of the computation, that we call alpha beta pruning. And in the next class we would be studying alpha beta pruning. Slides are available with you. These slides would be given to you. I think I'm on the slide number 11. There are 4 more slides available. Last slide would be this thank you slide. So therefore, essentially 3 more slides. I suggest you that you read this, and in the next class be prepared so that very quickly we can cover it. Okay. Any more questions? If you understand this thing, I'm done. I'm very happy that you understand all these things. These things are very important. We have seen various scenarios in which there are problems, and we have developed a solution for all these scenarios, that how to go ahead with the problem. Okay. Again, I have got the same question, sir. What are the syllabus for mid-sem? I told you that the last class last class was the final, and nothing from this class. Okay, I'm going to close this session by just pausing the recording.